disk operate.
Yeah, thank you so much. I really want to thank the organizers for like giving me these opportunities to speak here and putting this whole conference together and the whole month. Okay, so I'll title my talk now, All Endomorphisms of the Framed Little Disk Operate are Automorphisms. That's the result. So yeah, that's it. So first I'm gonna talk about, give some definitions, then I'm gonna give a bit of motivation and talk about like some older results. Older is like 3-4 years older. And then I'm gonna give some proof ideas for that result. Okay, let's start. So we've heard about the little disk operate all morning. So first of all, what are operates? So I'm not gonna define an operate, but the slogan is operates encode operations. And like maybe the best example of operations are multiplications. Okay. So let's give an example. That has been talked about a lot today. So it's the little disk operate. Okay, so what do we need to encode like multiplications or something? We need something like, okay, an operation takes like n inputs and gives an output, right? So we have like an input space. We also refer to that as n-array operations. In this case, it's denoted by ED of n. Okay. And roughly speaking, what lives in here are affine embeddings from a disjoint union of n disks into a disk. Okay. So let's draw one of those elements in an input space. We have a big disk, right? And then we embed some disks in there, but in an affine way. And then maybe the other thing is we number them. Okay. Let's squint our eyes a little. Okay, ED of n is actually equivalent to the configuration space of endpoints in R to the D. Okay. So that's like, okay, we take 3 guys and get 1 guy out. Okay, cool. But then the other thing is what we need for an operate. We need, okay, we have something where 3 things go in, but then we can also put like another number of things and then can do that operation again. So let's just draw it out to make sure what I actually mean. Right? Say we have a 3-array operation, and now instead of this guy, we want to do a 2-array operation. Let's do it. For ease, I'm going to take this one. And then we get out this guy. 1 and 2 we leave untouched. And then instead of 3, we have this guy. Okay, shrink it down. Forget that this one even existed. Just going to replace it by those 2 little disks, or even littler disks. Okay. Yeah, and of course, the reference to his program is like Fred Cohen worked on these a lot, as we heard about it in the morning, calculate their homology, right? So yeah. There's one more thing we have with operates. We have an sigma n action on each of those input spaces, ED of n. And that permutes labeling of disks. Okay, so far so good. And I promised that operates encode operations or multiplication. Okay, so what type of operation is this? And so I'm just going to say this is more like tangential to this talk. It's like a loop space multiplication. Or also, it's like an associative multiplication in spaces with some amount of commutativity. Okay. Okay, well, but the title doesn't say little disk operate, it says framed little disk operate, so that's our second example. And I like to denote it not only by ed, but I like to denote by ed SO of d to imply, well, okay, in a sense, the framed little disk operate is the little disk operate, and we have some sort of group acting on it and then somehow gets put into it, right? So instead of SO of d, we could put other groups there. Okay, but so what is the framed little disk operate? I'm just going to draw an element in the input space. Let's say we have something like this, right? But now we not only remember those affine embeddings, but we also remember an additional rotation. Okay. So yeah, this is just to like, okay, we imagine the framed little disk operator is like rotated in there, like the little disk, both of them. And they can be differently rotated. Okay. So it's ed, but with remembering rotations. Okay. And now this operator composition works the same, but it also multiplies rotation. And this rotation is, of course, given by an element of SO of d. Okay. Okay. So we care about endomorphisms and automorphisms. So we care about map of operates. So let's take two operates, O and P. A map in between those is a collection of sigma n equivariant maps. And they, of course, go in between all the input spaces. Okay. And then we look at this diagram. It's the obvious diagram we can draw, right? So we either first use F and then use a composition, or we first do a composition and then use F. Okay, commutes up to homotopy. Okay, so maps of operators, little disk operate, wonderful. So now one can ask, what is out of ED? What are the automorphisms of the little disk operate, even framed little disk operate? The problem is, this is a really hard question. Okay. So let's look at groups acting on the little disk operate to look at what we can compare it to. So all of the acts by rotation on ED. So we have a map like this, right? This is like maybe not so surprising. Maybe more surprising is that the group of homeomorphisms of R to the D also acts on the little disk operate. And except for the automorphisms of ED, it is the known largest acting group on the little disk operate. So we also have a map like this. So it's the biggest known acting group except for the automorphisms of ED. No. Ian asked me whether I'm going to describe that action, and the answer to that is no, I'm not going to do that. What is the point I'm making, though? They're like, in a sense, the homeomorphisms of R to the D and the automorphisms of ED kind of act analogous in some ways. So like, there's an analogy. Top D, homeomorphisms R to the D are local automorphisms of manifolds. Okay, and then we look at embeddings of R to the D into R to the D. They're local endomorphisms of manifolds. Okay. Now, what is out of ED in this picture? This is due to work of like this better. This is described in work of Pedro Bouvier de Brito and Weiss. Just like local automorphisms of configurations in manifolds. So this is not precise. The precise way would be a category of configurations. And then endomorphisms of ED. It's the same, but with endomorphisms, okay? So like somehow those two groups maybe not that different. There's another interesting behavior, which we're going to talk a bit more about actually. There's Kista's theorem. We look at the inclusion of the homeomorphisms of R to the D into the embeddings, self-embeddings of R to the D. This is an equivalence due to Kista. Okay, and similarly, we look at the automorphisms of the little disk operate. We look at how it lies in the endomorphisms. That too is an equivalence. This is due to Horel, Geoffroy Horel, Sander Coopers, Emmanuel Kranich. Okay. So now my theorem says that this map, we look at this guy for the framed case, take the inclusion, the endomorphisms, that this is an equivalence, as stated in the title of the talk. Okay. Just going to avoid this side. Don't know how high or low I can write. Okay, I want to go over some ideas for the proof. So this is a workshop on interaction between homotopy theory and group theory. So far, I have only talked about homotopy theory, but now we're bringing in some group theory as well. Okay. So the first step is, okay, somehow these are hard to understand, like endomorphisms of the framed disk operator are somehow hard to understand, but they actually correspond to maps like this. Okay, so we look at submaps of the classifying space of SO of D. And then, you know, by acting on it, we have this map. By acting on the disk operator, we have a map like this. We look at all self-maps which make this diagram commute up to homotopy. Okay. and these correspond. So this uses some infinity operatic methods and result by Alexander Coopers and Manuel Kranich. And most crucially, it uses that the endomorphisms of the little disk operate, no group action here, is equivalent to the automorphisms of little disk operate. So this correspondence crucially uses this part. Okay. Plus some like infinity operatic language. Okay. So now let's restrict to two array operations, right? Of this guy to the two input space. The two array operations are the d-1 sphere. So this diagram is still hard. We don't understand this group. Let's look at this guy. So by restricting to two arrays, we get a diagram like this. In fact, if every such diagram commutes, if every map F, which makes this diagram commutes, is already an equivalence, well, and certainly these will all be an equivalence, right? There should be more of these than of these. And then these are all equivalences. So the theorem I'm actually proving is that all self-maps of BSOD, which lie over the automorphisms of the classifying space of the automorphisms of the d-1 sphere, all such maps which make this diagram commute, they're already equivalences. Okay. So how do we do that? So let's call these F tilde. Okay. So how do we do that? Okay. If D is not 2 or 4, then SO of D is simple. It's a simple Lie group. And there's actually a result we know about self-maps of BSOD. Gonna write out the result. Okay, so the theorem due to Joukowsky, Oliver, and McClure from 1992, I believe. Okay, so if G is a simple, compact, connected Lie group, and we have an isomorphism. Okay, so we go from U times G Okay, so we go from some quotient of this product to the self-maps of BG. Homotopy class of self-maps of BG. I didn't define anything, so I'm first going to define the subsets. U is a subset of the integers. And this subset depends on the while group. Well, depends on the order of the Weil group of G. So this is easy to figure out. Those are, of course, the endomorphisms of G, and those are the inner automorphisms of G. Okay. And what do? We take a K, and we take an F. We map it over here to a composition. The homotopy class, we have the map induced by F, and here we have an unstable Adams operation. And what is a different way of saying psi K is an unstable Adams operation? Multiplication by K to the I in the ith cohomology BG with rational coefficients. So those are all the maps there are, and that's actually very good news. Thank you. Sorry. Yes. It's 2I. What was the, yeah. Okay. So let's do a quick example for my case. Okay. Let's stare at G equal SO of 2n plus 1. Let's call this subset here endomorphism, what in automorphism is called rep of G. And then these endomorphisms, what those inner automorphisms. It's not a very big set. It has, in fact, 2 elements. It has the trivial map and the identity. Okay, so like we don't have a lot of things that can happen. Okay, how do we use the diagram we had before? Where is it? This one. We need to use the diagram. This is kind of folklore, but it can be found, this result can be found in an article by Manuel Kranich and Oscar Randall Williams. There exists a certain characteristic class, sigma, in the 4th n cohomology, the classifying space of automorphisms of S to the 2n with rational coefficients such that this map a name. Such that this map in cohomology maps 4 of those characteristic classes to the Pontryagin class, nth Pontryagin class. Okay, and now this implies, okay, we look at where F in rational cohomology even can make those can map this nth Pontryagin class, we again obtain the nth Pontryagin class. Okay. Yeah, and this now implies that F can only be induced by the identity. So F needs to be an equivalence. So we're homotopic to the identity equivalence. Okay. Yeah. So for the other cases, so if D is if D is even and not 2 or 4, then there's a similar thing we can do. Instead, we look at the Euler class, not into the nth Pontryagin class. It's very similar. And also, this group has 1 extra element, but yeah, doesn't do much. If n is 2, then BSO2 is CP infinity. We can deal with those maps. They're not that hard. And then if n is 4, we have to do a bit more work, but not too much more. Yeah, that's my talk. Thank you for your attention.